All right, let us begin. If anyone can turn on the video, can you turn on the video if you can? Okay. All right. Good to see you guys. Okay, so let's begin. All right. So in today's lecture, and then just as a reminder from the last week, last week's class, which was done by Professor Yun, was on the ones on debugging tools, right? So you basically learned very basics of GDB, right? So in today, we'll learn a little bit more about debugging, specifically by looking into different cases of errors, right? So in this lecture, what you'll be learning, what you expect to learn, what you should expect to learn is given some errors, what kind of given some typical errors, right? So we'll talk about some typical errors, and given some typical errors, how we will be using our tools to debug them, right? So we'll talk about some representative error cases in this lecture, and we'll talk about how you address those cases. Okay, all right. By the way, the mid-semester course evaluation is due until today, right? Due today, so it's not mandatory, but if you have any concerns or suggestions related to this course, please use this opportunity. If you give us a feedback, we'll try to, if there's any issues or concerns, we'll try to address all of them, okay? In the second half of the class. So, okay. So it's fully anonymous, right? So don't be shy. Okay. All right, let's move on. All right. Okay. Good programmers know debugging takes as much time as writing the original code, right? Some people enjoy debugging because it's like solving a puzzle. Some don't, because it keeps you away from submitting your code, right? So good strategy for debugging is to write a code that can efficiently avoid bugs. Okay. Some popular strategies would be some good design, of course, and good coding style, right? Starting from indenting, even indenting, and how do you the names of your variables and things like that, right? So we've talked about this all along in this lecture, as well as 209, if you are taking 209, right? And checking the boundary conditions and using like functions like assertions, and so on and so forth, right? Okay. Some language features, some language features may help you in some cases, right? Like range checking of array subscripts, right? These things are done by the language itself when you compile, right? So it will be checked by the language or the compiler or the linker, right? And so that spit out a corresponding error or warnings so that you can fix them, right? Some language features are prone to generating bugs is like global variables, right? Global variables, which which are prone to error, right? We've talked about this before. Why? Because it can be changed. The value of the global variable can be changed anywhere in the program, right? Without you noticing it. Therefore, it's prone to error. And go-to statements, this is prone to error as well, because you can just jump around between the codes, and it's really hard to debug. And unrestricted pointers, meaning pointing at deallocated memory and so on and so forth. So unrestricted pointer means pointer that is pointing at some place that you shouldn't be. Okay, maybe that area could be something, that memory space could be a memory space that was deallocated, meaning freed, right? It can be some memory address that is never assigned, right? Some trash value, for example, some pointer value, which is not initialized, right, would have some trash value, right? Those are unrestricted pointers. And also automatic type in conversions are very prone to error, right? Let me just write an example. Like unsigned character. This is actually an example from 209. If you have taken it, if you are taking 209, just take this as a as a reminder, right? For example, if you say 255, right? And suppose you do like SX goes UX, right? So what this is actually doing, this code is actually doing, is actually changing this, right, UX automatically into UX, which is unsigned character, right? And this statement is actually changing the US automatically or implicitly. Automatically, some people call it implicit. Implicitly changing the type into signed character, right? And this actually makes the SX equal -1, right? And this is just one example. I'm pretty sure you have experience with this. And this is called automatic type conversions, right? Compared to implicit, what is explicit? When you do like typecasting, right? Like if you for instance, if you do character, right? So if you for example, let me put it this way. The other side is called explicit. So what is explicit? Is typecasting, right? Okay. All right. So this automatic type conversions can be done without you noticing it, right? And this is prone to error. Okay, let's move on. So so what if my program crashes, prints nonsense or hangs forever, right? Meaning it runs forever without finishing, right? Some novice programmers who are not familiar with programming or does not have enough experience typically blames compilers, right? I've seen many of these cases. I think I was doing the same when I was beginning to learn programming, right? And when your program don't run or it does not run as expected, so beginners typically blame the computer, right? But that's from my experience, that's unlikely. It's typically your problem that is causing a problem. It's typically your program that is causing a problem. Okay. All right. So experienced programmers know that most problems are likely to be your fault, right, or their fault. Right. So computers, they are pretty stable, and they have been verified by many professionals until now for a very long time, right? So if you face an error, then it's likely to be your own code. Okay. So most bugs are simple, especially for your assignments. Your assignments are pretty simple for, even simpler for this, but it is simple for EE209 as well, although it will get more and more complex as you move on to the end of the semester. But anyhow, so most of the bugs are simple. Okay, you should start from simple bugs. When you face a bug, I'm pretty sure you have experience facing a bug and debugging, right? Try to start simple, okay? Because most bugs are simple, right? So when you face a bug, it's likely to be simple. So try to think simple, okay? Okay. These are the steps that you can take, not step, ways that you can take. You can infer a bug with a stack trace debugging output. Like you can see the output error of the compiler, or you can do stack tracing. We'll talk more about this in the following slide. And it requires backward reasoning. So when you face an error, you should start thinking. Okay? So what happened? What did I just change? Right? And most bugs come from the recent change, right? So try to think about what changes that you have made, the most recent change that you have made, right? Start from there. Okay. Let's look at some easy bugs or common bugs here. Okay. Let's look at this one here. So what's going on here? So what is the problem in this code, in this very simple code? Okay. Well, let's look at the errors, right? These are error codes, right? This, by the way, displaying all the errors can be done by GCC option called minus W all, right? By the way, this W all is included in the GCC 209. Oops. If you're learning GCC 209, right? This W all is already included in GCC 209, so that you are able to read all the errors or warnings, right? So by using GCC with this W all option, you're able to see all the warnings, right? Let's look at the warning here. So it says here, %d expects argument type int, right? Printf, %d in printf is used to print integer type, right? However, argument 2 has a double type, right? See here, this one is the argument 2, right? Oops. Yeah, D is a double, right? As you can see here, right? So this is giving you an error. So, and also, next warning says %f expects double, but argument 3 is int. So this is int, right? Where this f is expecting a double. Okay, it's pretty simple. All you have to do is you have to switch it, right? Switch the two. Right? What else? What else? The scanf should take a memory address, right? As an argument. So this warning says the format %d in scanf expects integer pointer. However, n is just an integer. Right? Lastly, n is used uninitialized. So n does not take any number, right? So it's uninitialized. Okay, so uninitialized is a problem, is a potential issue because, right? Because it will hold some trash value, some random value there. Right? So that's the first step for debugging easy bugs, right? Which is to look for common patterns, right? Okay. What if the program hangs forever or crashes, right? If your program runs forever, so you've learned about GDB, right? You've learned the basics of GDB in the last lecture, right? Suppose you run with suppose your program hangs forever, meaning it runs forever or crashes. Then what you can do? What can you do? Right? It hangs forever, it runs forever, or it crashes without spitting compiler error. Then what we would do? What we would do, right? So you cannot use this strategy, right? If your program just runs forever, or if it just crashes without spitting any error, right? Right. So then what do? You can do GDB. You can run your program with GDB, right? In case your program runs forever, it will just keep running, right? You run your program in GDB, and it will run forever. Then what do? Is you type Control-C, okay, to incur SIGINT or interrupt to force the program to end, to terminate. Okay. You press Control-C, and then it will force the program will be forced to end, to terminate, right? And then you type something called where. You've learned this. We've talked about this in the last lecture of this last week. Okay, right? This takes you to the point where the program has ended. Okay, so if you type where, it will take you to the program, to the part where your program has ended, which is line number 37, which is running scanf. So basically, it was waiting for your program, the scanf was actually waiting for your input. All right. What about if the program crashes? Then what do? Okay. You run the same, but your program will, the GDB, your program runs and crashes, right? And you look at this error, okay? Oh, it's a segmentation error. And then what you can do is you can similarly run where, right? And it will tell you where the error has occurred. Okay? It occurred in scanf again. By the way, segmentation fault happens, for example, when you're taking, if you're doing something like this, right? Okay. Of course, this is a side note, but if you run your program like this, right? If you run your program like this won't run this won't compile in your GCC 209, because GCC 209 was configured to take any warning as an error, right? Right. But if you're not using GCC 209, if you're using GCC, right, it will compile with an error, right? Error like this, right? Okay. And then if you run it, this is you will run into this segmentation fault, okay, in scanf. Anyway, that was a side note. And okay, so we've talked about, these two are the ways to find where the error has occurred in case where your program just runs forever or it just crashes, okay, without spitting an error, right? All right. So what if? Then what if your program does not crash? Only when it runs on GDB. This might happen. Okay. So what this means is that when you run in your program, normally it crashes. However, when you run it on GDB, when you run it on GDB like this here, it does not crash. This can actually happen. Okay. Because running GDB incurs some overhead, which might make the program avoid crashing, to crash, right? So when you run on GDB, it does not crash, but when you run it, normally it crashes. Then what can you do? Then in that case, you cannot do this, right? This doesn't work because this is a way to find your error in GDB, right? In those cases, what you can do something called core dump. Okay, core dump is generating a binary file that contains the program state at the time of crash. By doing a core dump, it produces some binary file that stores the state of the memory at the time of the crash. Okay. All right. So the reason why it's called core is because traditionally core used to mean memory. Okay, in the past. Okay. So what you can do is so what we want to do is that we want to see the core. You want to read the core dump file. Okay. So you want, in case you don't want, so this is a case where you cannot use GDB, right? Okay, so this doesn't work. So what do? You just run it, and it crashes. The program crashes, and it will make a core dump. Okay. So we need to find a way. We need to learn about a way to read the core dump, right? Okay. Before we do that, we need to set our environment so that the core dump is enabled. Core dump is disabled by default, so you have to enable it. Okay. Okay. In order to enable the core dump, you need to change some option. When you run this on your command prompt, you see that the core size, by default, the core file size is set to 0. Okay, this means that the core dump is disabled by default. Okay, so you need to change this. This is the maximum value of the core dump file, so you need to change this. Okay. The command to change the core dump file size is this. Okay? ulimit with -c option, and you can you can input the size of the maximum core dump file in bytes. Okay, so this is 10 megabytes here. Okay. And then you run ulimit again, then you're able to see that 10 megabyte is actually set, right? And then you run this program again, and then the core is dumped. And then if you look into your directory, you'll see this core file. Okay? This is the core dump file. And you can read it using GDB. Okay, now you run GDB program core. Right? So this core file should come as a last argument. Okay. And then so this restores the memory state at the time of crash. And then you type where, and then you'll be able to see the point where the program crashed. Okay. All right. All right. Okay. So some other ways to deal with the bugs is read before typing. Okay. Don't just begin typing, right? Think about what you write and read as you type. Okay. So hastily changing the code to see if it fixes the code would waste time. Okay. All right. Don't just fix it right away, right? Think about it, take your time, read the code carefully, and then fix it. Okay. That's all it's saying. Okay. And if you just change it with hastily, without reading it carefully or thinking carefully, that might even make the condition worse, right? By introducing additional errors, right? All right. Take your time and return. Take a break and return, right? When you take a break and when you return, and you might be able to see the error that you wasn't able to see before. Okay, that actually happens a lot, right? You try to read it, right? Right? Especially when you don't have time, right? You start to read it and try to find your error. It's really hard. A lot of times, it's really hard to find, right? Because this is the type, the code is written by yourself. Then anything that's written by yourself, it's really hard to find, right? Hard to find an error, right? In some cases, if you take a break and come back later on, that is helpful at times, right? And don't make the same mistake twice. And for example, if you copy and paste some code from somewhere else, then you may forget the code has you may forget that the code has a problem, right? Don't debug it. Don't delay or procrastinate debugging, right? So you need to debug it now. Don't do it later, okay? And so like in the case for Mars Pathfinder, it had an error. So the engineers knew the problem, but they forgot to fix, right? So whenever you have an error, try to fix it at that point, right? Don't delay it. Don't say, okay, let me debug it later on. You'll very likely forget, right, later on, right? Okay. So when you find a bug, fix it at that point, okay? Another way is to explain your code to someone else, right? As we talked about this in the EE29, right? It doesn't even have to be a person, right? You can talk to your dog or cats or even your dolls and try to explain. When you try to explain your code, there's a chance that you might be able to catch the error in your code, right? Because you need to think about how to explain it. Along the way, you'll be able to find your error, right? It actually happens a lot. Okay, sometimes you have no clue on what's going on, and for example, you need to, if you have no clue what's going on, then you can make the bugs reproducible. Okay, bugs that do not manifest often are hard to debug, meaning that if it's not shown, it's hard to find, right? Hard to debug, right? So you need to see if you can construct an input parameter or condition. You need to find the condition to reproduce the bug reliably, right? In some cases, right, bugs come and go, right? There was some bug for some input, and then for some other input, there's no bug, right? This is really hard to debug, right? So in order to debug these cases, you need to find a condition or input parameters such that you can reproduce the error reliably. can also do divide and conquer, where we've talked about this in, briefly in 209. You can cut the input in half. We can start from the smallest. We can starting from the big input. You can cut the input into half and see if the error persists. If the error persists, that means the error is caused by the half, what is left, right? And then you cut down the what is left into a half again and over again until you narrow down the input into a very small size. Huh? All right. And you can start from the other way around, where you start from the very small input or code, and then you double it over and over again until you find an error, right? In order to, all these techniques are for you to narrow down to see which part of the code is causing an error, right? You might have this is important at times, because you probably have experience of finding an error message, for example, and the error is actually not there, right? The compiler says this line incurs an error, but it turns out that's not the part where it actually could incurs an error, right? This can happen due to many reasons, right? So you need to find a way, in those cases, you need to find a way to designate or pinpoint which part of the code is causing an error, right? By yourself, right? Okay. All right. And another way is to study the numerology failures, right? So see if the bug has some numerical patterns, right? So for example, it happens at any n characters, right? Then you might want to test around n, right? N plus 1, n minus 1, and to see if you can enforce the changes at nth character and n plus minus n minus 1th character, nth character, n minus 1th character, n plus 1th character, and so on and so forth, right? Okay. And another one is to display output to localize your search, right? So display more, basically putting more asserts or putting more printfs to display an output whenever you can, right? Another way, when you're doing so, one tip is to display a message in a compact fixed format, right? For example, you can output when you output an error, maybe you can use hexadecimal display, hexadecimal representation to for you to easily grab the corresponding messages, right? So printf will be everywhere. For example, let's talk about printf. Printf will be everywhere in your code, right? Right? But not all printf messages are for debugging, right? So maybe you want to differentiate your printfs from your printf that is for debugging from other printfs, right? Right? And one way is to use hexadecimal format, right? You can, of course, you can use any format that you'd like, but the point here is to differentiate your error messages from standard printf messages, right? In that way, you can grab it later on and easily debug, right? This becomes more and more important as your program gets bigger and bigger, right, throughout the semester. All right. Okay. Another way is to add self-checking code, right? To write a check function to see whether a code leads to weird state, and you can leave the code. You can leave the check code even after debugging, right? by using like these preprocessors, right? For example, let's look at this check function here. You can define a check function, right? Where if to check if variable 1 is bigger than variable 2, and whenever and it prints out variable 1 and 2, right? When you use printf, be sure to use fflush, right? So that the printf will not be will be printed right away, right? Okay. And then abort. Right? Note that these check codes can be left even after debugging, right? When you want to release the code, these check functions can still be there by using ifdef, right? So for example, maybe you want to, for example, you can do, right, shop ifdef debug, okay, debug, and then you can do and if here, right? And in your beginning of your code, you can do define debug. In the beginning of your code, you can just do this, and then by doing this, this will enable this part of the code, right? Okay. All right. And after you're done debugging, all you have to do is, without removing this part, all you have to do is comment out, oops, just comment out this line, this one line, right? Right. And this will disable all these error checking codes, right? Okay. And this is actually a very popular way of programming. All right. Okay. All right. What if nothing works? Meaning, what if your logic is wrong? Well, this is if the error is logical error, right? If simply meaning that it's simply a error in your algorithm, right? And then it's, then you have to then you have to manually find it, right? Where using GDB can be help, right? For example, let's look at some of the examples here, right? So for example, this, right? Right? Well, because of the precedence, well, this will be this is an error, right? And this will always be a false, right? Okay. Because ++ is of higher priority, right? It will this will actually always be false, right? What about this one, right? You should, this should actually, at least this is a typo for this, right? Right. This is actually a typo for this, right? These isn't something that is, this isn't really this is really a error by yourself, right? It's your error, right? This is not something that can be checked by checked by the compiler or the computer, right? Right. This is something that you have to manually find and fix. Okay. What about this one? Well, this is a useless code. This is doing nothing, right? Because you have semicolon at the end. So this is actually doing nothing. Okay. What about this one? Well, do you really want to do this, right? do you really want to do this? Because this is the same as ai equals 0 and then 1, right? This is actually adding 1 after assigning 0, right? So is that really what you want to do, right? Right? Okay. Or other errors could be like local variable that hides a global name, right? So if you have a global variable and you have another local variable with the same name, and you access the local variable within the function, then within a function that it actually hides the global name, right? Right? Then you'll be accessing the global variable as opposed to local variable, right? Okay. Or global, you're accessing global variable in the local scope. Do you really want to do that, right? Those are the potential parts that could potentially incur errors. There's a okay. So there's a question of what does this mean? Well, this means nothing. It means nothing, but this always be true, right? Yeah, I think you were asking because of this, but this is yeah. I think this is a pretty meaningless. This is always true, and it's kind of meaningless code, but but this is just always true. Okay. All right. Oh, okay. So you're saying okay. Why isn't it x and 1? Well, it's just a bitwise operation and the logical operation, right? So I guess your question is why would anyone wants to do this? Is that is that what you're saying? Yeah, I think this was a typo. I think this should be what originally wanting to do this. Yeah, I agree. It's just kind of weird code, but yeah, I don't think this was. I think it was we're trying to should be this. Oh, okay. So okay, you did not know this was an operator. Okay, so this was a yeah, it's a bitwise operator. So it still works, but kind of meaningless. But anyway, so let's move on. All right. All right. Let's talk about non-reproducible bugs. Okay. So it's sometimes if it's not deterministic, meaning okay, with the same input, you run the program over and over again. Okay. But it's sometimes with the same input, you run the program over and over again. But sometimes it causes an error and sometimes it doesn't. Okay, this is what this is saying. Okay, and in that case, it's not likely to be a bug in your program. Okay, and it might be maybe the chances that your code might be using information that changes each time the program runs. Okay. For example, maybe you're taking the system time to do something, right? To run your program, right? Or whatever. Maybe you're taking some your code is taking some parts of the something that changes over time. Okay. You need to check in order to avoid this problem. You need to check whether all variables have been initialized. Okay. All right. So again, why? Because if you don't initialize a variable, then that will hold some trash value, some random trash value, right? Since it's random, it can cause non-reproducible, non-deterministic bug, right? So it holds some random. It can hold some random value that can change every time you run the program. In that case, it will cause an error at some times and might not cause an error in some other times. Okay. When bugs disappear, if a debugging code is added, it may happen, right? So there's a bug. So you run like a printf or assert functions to find to debug, and then all of a sudden the bug goes away. That actually can happen, and in this case, it's likely to be a problem of dynamic memory allocation. Okay. For example, maybe you're writing a memory. You're writing outside the allocated memory. Okay. And this behavior will change, could change, if you add a debugging code like printf. Okay. All right. All right. What if your program crashes in the middle of nowhere? Meaning, okay, maybe it crashes, and the line where it crashes, you check the line where it crashes, and it's far away from anything that could be wrong. It's a very simple statement where nothing can go wrong, but it still crashes there. Okay, what does that mean? Okay. Maybe, most likely, the problem is overwriting the memory that isn't used much until much later. Okay. Okay. So you overwrote somewhere, right? And then you use that part of the memory long time after, much later. Okay. Okay. Or you return an address of a local variable as a pointer. Okay. For example, like this. Right? This function returns a buffer pointer, right? Which points to the local array. Okay. And then as we learn, right, when we return from this function, this memory space is gone, right? Because the local function uses stack, right? And as soon as we return, it's gone, right? Right? But if you use this later on, this will cause an error. Okay. All right. What about? Wait a minute. All right. What about this one? Okay. Is there anything wrong with this code? Anything wrong? Okay, one second. All right. Yeah. Well, there can be many. Well. Okay. So. Okay. So the problem of this code is that, well, this next P. So P will be. Okay. So the problem with this code is that it will run forever. Okay. Does it work? Not forever. It will free multiple times. All right. Okay. All right. So what will this code do? Well, it will initialize the P to list P, some pointer defined somewhere else, right? Okay, and then it will free P. If it's not null, of course, let's assume that it's not null, and it will free P. Okay, all right. Assuming that list P was holding some malloc allocated memory space, pointing at a located memory space, then this will work, right? After this is done, what will be done is, and then you put input next P into P, right? Right? Which is not even initialized, and we'll try to free that P. That will cause an error, right? Okay. Right. I guess there are many different ways to solve this issue, solve this problem, but I guess there are many ways, but one way to fix this is, for example, we can remove this, right? And we can say, for example, next. Maybe we should remove it. Okay, next P. There are many ways to solve this. Say maybe if assuming that this is a linked list, and if the structure has the pointer next P, you can also do this, right? Right, and you can remove this, right? Right, there are different ways to solve it. Okay. All right, let's move on. So okay, some debugging techniques. Okay, let's talk about debugging memory management. Okay, some debugging techniques are specific to dynamic memory management, like malloc, calloc, realloc, and free. Okay, right. Let's look at this example here. Okay, let's look at some of the familiar or very typical error that is, that happens a lot when you're using dynamic memory allocation, right? So one is a dangling. This is specifically these are examples of dangling pointer. Okay, if you have maybe okay, you define integer pointer P, and without assigning a memory space, you just input some value. Okay, so this is a dangling P is a dangling pointer because it's it's not pointing at anywhere, right? It's just holding a trash value, right? And it has not been allocated to a memory, right? Therefore, if you just try to input some value, it will cause an error, right? Another case is that, well, you free the P, you've allocated some memory address, but you freed it, deallocated it. Therefore, P is not pointing at anywhere, meaning that P is not pointing at a valid memory space. And now you're trying to store some value within that address space, and that's also an error. And all these cases are a dangling pointer, meaning pointer is not pointing at a valid space, right? Okay. Okay. Some other examples. These two examples are actually duplicated from EE209, but in case you did not, you have not taken EE209, or in case you're not taking EE209, right? You can for example, you assigned memory malloc to a same P, right? This is called aliasing, meaning the same name for different memory addresses, memory spaces, right? And the first memory space will not be accessible anymore, right? Because you lost the address to the memory space, right? And that can be found by some tools like Valgrind, right? Another typical error is that you free the same space twice, right? And that can be found by changing the variable malloc check, right? All right, okay. Let's continue on with this typical errors. All right. Okay. For example, if you do this, you try to copy this into this, and in order to do so, you allocate some address where the space, where the size of the space is found by string length. Where this allocate, and then you try to copy S1 into S2. This doesn't work because string length returns the size of this string, excluding the null character at the end, right? Okay, so the string length will return 1, 2, 3, 4, 5, right? This will return 5, right? Where you actually need 6 bytes, right? Okay, what about this one? Well, this mallocs, if you do malloc size of, oh, never mind. Size of S1 actually returns the size of character pointer as opposed to size of the string, okay? So the pointer is 8 bytes. Four bytes for 32-bit machines, and 8 bytes for 64-bit machines, right? So in case you're since copying the string needs 6 bytes, right? For you're lucky if you're using 64-byte machine, right? Since then S1, S2 will be allocated with 8 bytes, which is sufficient. However, if you're using 32 bits, then you're out of luck. Okay, similar here, right? If you do this, and this will actually return the same 8 bytes for 60-bit machines and 4 bytes for 32-bit machines. And if you try to allocate double into P, then and if you're using 32 bits, you're out of space. Okay, you don't have sufficient space. Okay. 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 Continuing on. If you have a segment fault, you try to make it happen within GDB, and then issue GDB where command to find where the segmentation happened. But keep in mind that the line that's reported by the GDB may not necessarily be the actual line that was causing an error. Okay. If you have segmentation errors or any error that segmentation errors and any error that was done by the caused by memory management, try to inspect, the memory management, dynamic memory management functions, right? Calloc, malloc, and so on, right? Okay. Another way to make sure that it locates enough memory, and another way is to temporarily hard code the call of malloc calloc, right? So for example, try to put sufficient error, right? Large number of bytes into a malloc, and see if it gets rid of the error, the segmentation fault, right? In that case, you should. That indicates that you should allocate more bytes to that malloc, right? Right. Right. You can another way to debug dynamic memory management issues is temporarily comment out each call of the free function in your code. Maybe you're doing duplicated free, right? So try to comment out each free one by one, right? See if that removes the error, right? Maybe you are freeing, you're doing duplicated free, or maybe you're freeing a memory that should not be freed, right? Of course, using free is a good practice because it avoids, it avoids memory leakage, right? However, there can be issues by free. Maybe you're doing a duplicate free, and maybe you're doing you're freeing something that you should not be free, right? Okay. So try to comment out each free one by one and see if that removes the error. If so, you're you're either freeing it, duplicated freeing it, or you're freeing a memory space that should not be freed. All right. Okay, that's it for today. And the homework for today until the next Friday is as follows. It's pretty simple. You can read it yourself. Basically, it's an open-ended problem where there's no right or wrong. We just want your input of debugging, right? It could be GDB or it could be something other than GDB. Okay, right? If you're taking 209, tell us about your experience in doing assignment 2 of EE209 and how you used your debugging tools and how you debugged your code. Right? If you're not taking 209, just tell us your what techniques that you used in lectures 5 and 6, and that would be most useful to you, and explain, and so on and so forth. Right? Okay. All right. I don't think you should have any question on this. Okay, right? So that's it for today. Thanks for listening. Of course, you're free to stay for questions, right? Okay. And for those of you who are taking 209, good luck on your midterm, right? Okay. All right. Thanks. Bye-bye.
Professor.
Yep. Go ahead.
Could you explain the first box on slide 15 again?
First box. First box. Okay.
Yes.
This one here?
Yes.
Okay. So this function actually declares a local variable of buffer array, right? Character array named buffer, right? And it returns the name of the array, which is actually a pointer, right? So it returns a pointer. So meaning when you use MSG function and it returns the pointer of a local variable, right? And it will use later on in this code, you will use this return value, right? Maybe you'll try to write some value into this memory space or something, right? And that will cause an error. Because when you at the time you return from this function, this data is gone. Okay? Because this is a local function, and this is when you call a local function, this memory space will be allocated until the function returns. When it returns, all the memories that is related to this local function, right, which includes the local variable, is gone. So you should never reuse it. Okay, never try to use it. Okay, once you return, all the values related to the local function is gone, including local variables.
So the buff pointer,
Yep.
I wonder, isn't it very similar with table create function in linked list?
I don't quite remember the code there. Let me try to go back. You mean you? So you're taking 209, right?
Oh, yes.
Okay. Okay. Let me go back to. Let me try to pull it up. You mean the hash table, right? I mean the
No
hash table,
matter.
right?
Yes, yes, yes.
So let me see. Create here. Okay. Is this it?
I wonder, we still could use the pointer t,
Mm.
but we can't use the value in t if we define that in the function, local function.
Oh, okay, okay. I see why you are. I see why you are confused. So the difference is you're doing a. Okay, the difference is that you're doing a malloc here or calloc. So you're doing a calloc here, and so basically the memory. So your question is, if you when you return from this function table create, shouldn't this be
Yes.
gone as well, right?
Yeah, yes,
That's
yes, yes.
a, that's a good question. Actually, no, this remains. And this, yeah, I see why you're confused. So if you do malloc or calloc,
Yes.
this memory space is actually in the heap. And so bottom line is that this memory space is still there. This memory address, this memory space is still allocated, even when you return from the function.
Oh,
That's the bottom line. And why? Is because this memory space is located in a heap, something in a place called a memory space called a heap, where the local variables, right?
yes.
The local variable is stored in something called a stack. Okay.
So difference is the location.
The technically speaking, the difference is the location and how the stack and heap are managed by the computer system.
So,
Okay, so let me.
yes.
I think this is a pretty interesting question. Okay, so all right, so this is a global. This is local variable as well, right? I think I know why you're
Yes.
confused here. This is a local variable, right?
Yes.
And it returns t. And it seems like since this is local variable will be gone, right?
Yes.
However, this the return value is t, right? Which is the memory address, right? And this memory address points to what was located by calloc, right? And this memory space lives even after you return. So when you do this, okay, this pointer itself, right, will be gone after you return. Okay,
Okay, I got it.
do you understand? So in this
Yeah, yeah.
stack, stack, let's say this is a stack. When you call this, you will have a function, a t, right? A pointer t value t, right? Which is a pointer, and this is 8-byte address, the 8-byte space, right, in the stack, right? And this will
Yes.
point to a heap where a heap holding a table, right?
Yes.
Structure, right?
Yes.
right? Okay, when you return, this will be erased. You're correct. However,
So
how
yeah,
we'll be
yeah.
using it, what we'll be doing is, okay, in the main program, what will you do? You will have some pointer, right? Pointer P, right? You'll have struct struct table pointer P, right? Let me rewrite.
Yes.
This is a terrible writing. Let's say it's a void main, right? And you'll have some struct table struct table pointer P, and what you do is this, right? Create, right? This is what you do, right? And then use P to access the table, right? Later on, right? Is that correct?
Right. Then the table create function just return the such pointer address number, not the pointer itself.
Not the pointer itself. Exactly.
And every stack memories are gone after.
Yes, but the heap
function.
remains until you free.
Oh, okay, I see.
I think that was a great question. I think I didn't think this would be confusing, but after listening to your question, yeah, this could be confusing.
Thank you, Professor.
Okay, thank you. Any other questions? Okay, I'll wait for another 5 minutes. I'll mute myself and turn off my video. If you have any questions, I'm still here, so please chat. So if I don't have any questions in the next 5 minutes, I'll end the session today. Thanks. Okay, I guess there are no other questions. I'll end it here today. Thanks. Bye-bye.